Hello everyone. Today we are going to solve another important question from module 5 group theory. So the question is, define group, show that fourth roots of unity is an abelian group. So first of all we have to know that what is a group. Group is nothing but it is a set G with a binary operation multiplication such that it satisfies four key properties. First, closure. Second, associativity. Third, identity element. Fourth, inverse element. If all four properties are satisfied, then only it is known as a group. And also, if it satisfies commutativity, means the order of operation doesn't matter, then it is an abelian group. So one by one we will check if the fourth roots of unity is an abelian group or not. So now let's look at the fourth roots of unity. These are the complex numbers that satisfy the equation z to the power 4 equal to 1. The four solutions that can be, we get are 1 comma minus 1 comma I and minus I. Let call this a set G equal to 1 comma minus 1 comma I comma minus I. We will consider multiplication as our operation. Let us check if this set satisfies all the group properties or not. So first one is our closure property. What is closure property? Closure property is nothing but multiply any two elements. The result is still in set. Means, for example, we will say that if I is an element and I is also of the same group, so the result will be minus 1, as we all know that. So here in the set G, I is in the set G and 1 is also in the set G. So I multiply with I equal to minus 1. So it means that it satisfies closure property. Like I multiplication with minus 1 equal to, sorry, this is minus I into minus I equal to 1. Minus 1 into minus 1 equal to 1. So all these multiplication is also in the set G, and all the results of this multiplication is also present in the set G. So all the results belong to G. So it satisfies closure property. So now we will go to second property, associativity. This is an important one. We need to check if A multiply with B multiply with C equal to A into B into C, like this. Now in our case we are using complex numbers multiplication, which is inherently associative. This means that no matter how you group the numbers when multiplying, the result will always be the same. So for all the elements in G, here all the elements in the G is associative, automatically true. So it simply satisfies the associative property. Now we will go to the third, identity element. Now we will go to the identity. identity element is 1, because a into 1 equal to 1, we all know that a equal to a, sorry, this is a multiply with 1 equal to 1 multiply with a equal to a, which always belongs to G, so it satisfies identity metric. Identity element. Now we will go to the fourth one, our invert element. In this we will check the element has an inverse or not. So here our first element is 1 to the power inverse equal to 1, which is also present in G. So minus 1 to the inverse equal to minus 1, it is also present. So minus I to the power minus 1 equal to minus I, it is also present. Minus I to the inverse equal to I. So all the so each element when multiplied with its inverse gives 1 the identity. Now we will check commutative property. If this property is followed by this, then only it is called as an abelian group. So what is commutative property? If a into b equal to b into a, then only we can say that this is an commutative property. It follows commutative property. So according to our set G, I into 1 equal to 1 into I, simple, minus I into I equal to I into minus I. So we can see that this equation follows the commutative property. So it follows, it satisfies the commutative property. Hence we can say that this all five conditions are satisfied, including commutative property. We conclude that the set G equal to 1 comma minus 1 I comma minus I under multiplication forms an abelian group. Thank you.